Hi there, and welcome to this lesson on Further Pure Mathematics 2. In this lesson, we're looking at what are called loci, and they're loci of complex numbers. Now, what is a locus? Loci, by the way, is just the plural. Locus is the singular. A locus is a drawing, and it's a drawing which shows the possible locations of a point, given certain restrictions about where that point might be. And there are two possibilities. Sometimes a locus is a line or a curve, and the point has to be located somewhere on that line or curve. The other possibility is that a locus is indicated by a shaded region, and in that instance, the point has to be located somewhere within that region. So, for example, if Z is represented by the point P, where the modulus of Z is equal to 5. We're asked to sketch the locus of P on an Argand diagram, and we're asked to find the Cartesian equation of the locus of P. Okay, bearing in mind what you know about the modulus and the definition of the modulus, I'll let you have a go at doing this yourself first. So pause the video, have a go, and come back to me when you're ready. Okay, let's have a look at this together. So we've got the modulus of Z is 5, and we're asked to sketch the locus of where a point could be under that restriction. Now, what does that mean if the modulus of Z is 5? It means that the distance from the origin to Z has to be 5. But Z could be anywhere you like, as long as the distance from the origin to it is 5. So it could be here, but it could be anywhere else, which is exactly 5 units from the origin. So it could be anywhere on that circle. Now that is the locus sketched. So if you're asked to sketch a locus, that really is all they're looking at, looking for. Part 2 asks to find the Cartesian equation of the locus of P. Well, we've got a circle. The center is the origin, 0, 0, and the circle has radius 5. So in this instance, we can just use normal geometry to immediately say that the Cartesian equation must be x squared plus y squared is equal to 5 squared. What happens in general with that sort of situation? Well, the general case would be where Z is represented by the point P, and the modulus of Z is equal to R, any number R. Again, what is the locus of P? You don't have to sketch it. Just write down in words what the locus would be, and then write down what the Cartesian equation of the locus would be. Have a go, pause the video, come back when you're ready. Okay, it's exactly like the first question, this. Once again, we'll get a circle. The circle will still have center the origin, and the radius will be R, whatever R is. And the Cartesian equation will be exactly the same as before, except we'll have x plus y squared is equal to R squared. And that's the general formula, if you like, for a locus of that form. Okay, example 3, slightly different. If Z is represented by the point P, where the modulus of Z minus 2 plus 3i is equal to 3, what will we have in this instance? So again, we're asked to sketch the locus of P, and again, we're asked to find the equation of the locus of P. Have a go, pause the video, come back when you're ready. Okay, what's going on this time? We're asked to sketch the locus first of all. What is this saying? Well, there are two ways of thinking about this type of question. Both are perfectly fine. The second way that I give you is a better general method. And for harder questions where the first method doesn't work, the second method is the one that you should always fall back on. But first of all, you can think about this question geometrically and exactly what that is saying. And what it's saying is that Z minus 2 plus 3i equals 3 means that the distance from Z to the fixed point 2 plus 3i is equal to 3. So you've got a fixed point, 2 plus 3i, and the distance from Z to that point has to be 3, which is extremely similar to the first case that we had. If the distance from P to 2 plus 3i is always 3, then P must describe a circle again, but this time the center will be 2 plus 3i, and the radius is the same as before. The radius will be 3. So geometrically, we can get straight to the answer. We've got a circle center 2 plus 3i, radius 3. The alternative method, which is the better general method on more difficult questions, is to think algebraically what is going on. Now, algebraically, what we always do is let z equals x plus yi represent the point P. So just a general complex number. And then the question, z minus 2 plus 3i equals 3, becomes x plus yi minus 2 plus 3i equals 3. We've just substituted in for z. Then we collect the real parts and the imaginary parts together, and it becomes the modulus of x minus 2 plus y minus 3i equals 3. And then we just use the basic definition of the modulus, which is that to find the modulus, you'll square the real parts, square the coefficient of the imaginary part, add them together and square root it. So the square root of x minus 2 squared plus y minus 3 squared must equal 3. That is just the definition of the modulus. Squaring both sides will give us x minus 2 squared plus y minus 3 squared equals 3 squared. And algebraically, that is a circle. It's a circle with center 2, 3 and radius 3, exactly the same as we had using the geometric method. So by either method, we've got a circle, center 2 plus 3i and radius 3. We'll now do a sketch of the locus, and it'll be something like that. The center is 2 plus 3i, the radius is 3. Now, whilst they don't want you to draw accurate scales or use graph paper or anything like that, they do want the key features to be accurate. And there's two important key features on this. The first is this: the circle has got radius 3. The y coordinate at the center is also 3 because we've got 3i here. Now that means that the circle is going to touch the x-axis. It won't cross it, but it will touch it because that distance is 3, whichever way you look at it. And the other thing that matters is that the circle crosses over the x-axis and has 2 crossing points. And we know that because the x value here of the center is 2. So if the radius is 3, it must go beyond the x-axis and come back. So whilst they don't have to be perfect, these sketches, key features do need to be correct. Part 2 asks us to find the Cartesian equation of the locus of P. Well, we've got a circle center 2, 3 and radius 3. And using the algebraic method, part of that method is that you automatically do get the Cartesian equation, which was x minus 2 squared plus y minus 3 squared is equal to 5 squared. Okay, we'll have a quick look at the general case. And the general case is where P is represented by the modulus of z minus any point, a plus bi, and is equal to any radius r. So in the general case, what's the locus of P? And in the general case, what's the Cartesian equation of the locus of P? Again, I'll let you have a go. Pause the video. Come back to me when you're ready. Okay, what is the locus of P? Well, it's a circle again. This time, or in the general case, the center will be whatever this complex number here is. So if it's a plus bi, whatever that is, that will be the center of the circle. And as in all the other questions, r will give us the radius of the circle. What's the Cartesian equation of the locus? Well, if we know the center and we know the radius, we can write down the Cartesian equation straight away. And it'll be x minus a squared plus y minus b squared is equal to r squared. Okay, example 5, slightly different question now. Given that z satisfies the modulus of z minus 3 equals 5, the first part, same as we've been doing up to now, sketch the locus of z. And then we have to find the values of z that satisfy both these conditions. First of all, that it's on the locus, z minus 4 equals 5. And secondly, that the imaginary part of z equals 0. You need to think about what that means. And then part 3, again, that it's on the locus, the z minus 4 is equal to 5, but this time that the real part of z equals 0. I'll let you try and work out what's going on yourself first. So pause the video, have a go, and then come back to me again when you're ready. Okay, let's have a look. The first thing we're asked to do is sketch the locus of z. I mean, it seems slightly strange because we've just got a real number here. It's 3 plus 0i. Well, 3 plus 0i is on the x-axis at 3. So 3 on the x-axis will be the center of this circle, and the radius of the circle will be 5. So we'll get something that looks a bit like that. The center will be at 3, the radius is 5, so it is going to cross over this side of the y-axis. That's the locus. Part 2 says find the values of z that satisfy both the modulus of z minus 4 equals 5 and the imaginary part of z equals 0. The first thing is just saying you've got to be somewhere on the circle. The second thing is saying that the imaginary part of z has to equal 0. Now, where does the imaginary part of z equal 0? Well, the imaginary part of z equaling 0 is exactly equivalent to saying y equals 0 with normal Cartesian geometry. The imaginary axis is the y-axis. The real axis is the x-axis. So what we're saying here is the same as asking what happens if y equals 0. Now, if y equals 0, we're going to get these two crossing points on the x-axis. So if the imaginary part of z is 0, we're talking about the intersection points of the locus with the x-axis. And there'll be one point here at -2, and there'll be one point here at 8. And we know that because the radius of the circle is 5. So 3 plus 5 gives us the 8, 3 take away 5 gives us the -2. Part 3 says something very similar. Oh, the answer, first of all, you just write down the answer is, and in complex number form, you'd say z equals -2 and z equals 8. There is no imaginary part. Part 3 asks us something similar. It says, what happens if both the modulus of z minus 4 equals 5, but this time the real part of z equals 0? Well, if the real part of z equals 0, that is the equivalent to saying what happens if x equals 0. And if x equals 0, you'd normally get the crossing points on the y-axis. So in this instance, it's the intersection points of the locus with the y-axis or with the imaginary axis. Now, to find those, we need to go back to the equation of the circle. And in this instance, the circle will have equation x minus 3 squared plus y minus 0 squared, because the center is on the x-axis, so just plus y squared equals 5 squared. That's the equation of the circle. We're being asked what happens when x equals 0, so we'll just have to substitute x equals 0 into the equation of the circle, and that'll give us 0 minus 3 squared plus y squared is 5 squared. That gives us 9 plus y squared is 25, which means y squared equals 16, and y equals plus or minus 4. So this point here will be plus 4, and this point down here will be minus 4. And writing down the answer, that means the answer is z equals either minus 4i or plus 4i. That would be these points on the imaginary axis. Okay, the last example is quite long. Example 6. Given that z satisfies z plus 2 minus 2 root 3 equals 2, first of all, we'll have to sketch the locus of 2. Then we're asked to find the minimum value of the argument of z, the maximum value of the argument of z, the minimum value of the modulus of z, and the maximum value of the modulus of z. Now, I will let you have a go at this yourself, but before you do, something very important before you ever begin this question. It's not written in the standard form. The standard form is z minus some complex number within that modulus. So we need to rewrite what's in the modulus to z take away whatever the appropriate complex number is. So that's how you begin. Part 1 you should be able to do, and I'll let you have a go at the other parts yourself. Pause the video, come back to me again when you're ready. Okay, let's have a look at this question. So part 1 is sketching the locus, and as I said, we do need to change it into the standard form, z minus a complex number. That does matter. So it becomes z minus 2 plus 2 root 3 equals 2. And then we can use the general formula, the general idea, which is that will be the center of the circle, and that will be the radius of the circle. So we've got a circle which has center minus 2 root 3, and it's got radius 2. That is what it would look like. Now, if the radius is 2, it will touch the y-axis, because again, this center is at minus 2 on the x-axis. So that distance will be exactly 2. 2 root 3 is bigger than 2, so the circle will not cut the x-axis. It will be above the x-axis as it's drawn there. Now, part 2 asks us to find the minimum value of the argument of z. Now, what that is saying is, of all the points on that circle, which point would give you the minimum value of the argument of z? And the argument of z is the angle going anti-clockwise from the real axis, from the positive real axis. So we're asking which point on the circle will make that angle the smallest. Now, by inspection, the imaginary axis, the y-axis, that is the smallest the angle can ever be. So if we had this point right here, then the angle would be exactly 90 degrees. The argument of z would be exactly 90 degrees. So by inspection, the minimum value of the argument z is pi by 2 radians, 90 degrees, looking at that point there. What about the maximum value of the argument of z? Well, we're looking for the point on the circle which will make the angle going anti-clockwise as big as possible. Now, it'll be that angle there. So if we draw a tangent to the circle from the origin, then that angle going anti-clockwise around to the black line, that will be the biggest that the angle can ever be, that the argument of z can ever be. So we need to find the whole of that angle. And the method we use for doing that is just to look at this bit with the circle. Tangents are useful because the line from the center to a tangent meets the tangent at 90 degrees. So if we draw in these radii, then we know we're going to get right angles here and here. I've called this little angle here theta, and by the symmetry of the thing, it must be exactly the same as that angle there. So they are both theta. We'll use trigonometry in order to find theta. This distance is 2 because the center is at minus 2. So that must be 2. And this distance is 2 root 3 because again, the center is at 2 root 3. So to find theta, we'll do inverse tangent of 2 root 3 divided by 2. That gives us pi by 6 radians. Now we actually need 2 thetas. So 2 theta will be double that, which is pi by 3 radians. The argument of z is made up of those 2 thetas plus the 90 degrees. So we also need to add to that pi by 2 radians, and that gives us a total of 5 pi by 6 radians. So therefore, the maximum value of the argument of z will be 5 pi 6, which is that total angle going from the positive real axis anti-clockwise. Now, what about the modulus? We're asked to find the minimum value of the modulus of z. Now, what is that? It's the minimum distance from the origin to any point on that circle. Now, that will be the distance from the origin to that point there. Now, we can find that point using Pythagoras with this triangle and our knowledge that the radius of the circle is 2. So the distance we want, which is from the origin to this near point here, will equal the whole of the distance from the center, take away the radius, take away 2. And that's equal to the square root of 4 plus 12 when we use Pythagoras on this triangle. The top distance is 2, and that distance in the y direction is 2 root 3. So that gives us the square root of 4 plus 12 for the whole of the diagonal. Take away the radius. which is 2. That simplifies to 4 minus 2, which is 2. So that is the minimum value of the modulus of z. The maximum value is extremely similar. The maximum value is the distance to the point on the opposite side of the circle. That's the furthest that you could ever be from the origin. So it's the distance from the origin, this point here, on the opposite side of the circle. That'll be the maximum of the modulus of z's. And it's the same as before. Using Pythagoras, we find the distance from the origin to the center of the circle. But instead of taking away 2, we'll need to add on 2. So as before, we'll get the square root of 4 plus 12 using Pythagoras on this triangle. But this time we'll have to add 2 to that. That gives us 4 plus 2, and that gives us 6 for the maximum value of the modulus of z. Okay, that gets us to the end of this lesson. If you have the textbook, then turn to page 52, and exercise 4a, questions 1 to 5 are on this type of question that we've been doing. Thank you very much for listening, and cheerio.